First of all, can you hear me well enough in the back of the room? Yeah, it's okay. So I'm going to talk about coupled assimilation developments for operational numerical weather prediction at ECMWF, and I want to start to acknowledge my co-authors working in the coupled assimilation team, and also in the Earth system assimilation section and the Copernicus department of ECMWF. So I want to thank all of them. We are doing numerical weather prediction, and for this we are using an Earth system approach. So we account for different components in the Earth system, the atmosphere, of course, and land, ocean, wave, and sea ice. And for each component of the Earth system, we have a dedicated model, and we have a dedicated data assimilation system. And for numerical weather prediction, for the forecast, we use coupled models for the forecast itself. And for data assimilation, we are moving toward coupled assimilation. And depending on the system we have for numerical weather prediction or reanalyses, we don't have the same degrees of coupling between the different components. So the objective is to develop coupled assimilation to provide consistent initial conditions between these different Earth system components of the coupled model, and also to have a consistent coupling approach for reanalyses and numerical weather prediction at medium range and seasonal range. We also need to have a very good consistency between the coupling approach we have between land atmosphere and ocean atmosphere, for example. We don't want to do something completely different for land atmosphere coupling than for ocean atmosphere coupling. So we need to have a global approach of the coupled assimilation implementation. And this also requires some infrastructure consistency for the different components. And for example, the point is, since we use different data assimilation systems for each component of the Earth system, we need them to be able to talk to each other efficiently in an operational environment. The ocean system needs to be able to work on the same file system, for example, than the atmospheric data assimilation. We need to use the same observation acquisition and the same observation interface, which is a very important point as well. Currently, in our system, the ocean doesn't use the same interface to the observation database than the atmospheric data assimilation system. So when we want to have quasi-strongly coupled assimilation with cross-covariance exchange, we need to have a common interface to the observations. So we are dealing with major infrastructure developments when we implement coupled assimilation in our system. And we also want to have some modularity of the coupling between these different components. We need to be able to switch off one of these arrows. We need to be able to run, for example, a land reanalysis at high resolution without without the rest of the system forced by the atmosphere. And we need also to be able to switch off the coupling between the ocean and the atmosphere. So we need modular and flexible coupled assimilation implementation. So before I really start, I want to tell about coupled assimilation terminology, because there is a large diversity of vocabulary used for coupled assimilation that you can find in the literature. So what we use at ECMWF is a terminology defined by Steve Penny. After the coupled assimilation workshop we had in Toulouse in October 2016, a white paper was written about coupled assimilation for integrated Earth system analysis and prediction, goals, challenges, and recommendations. And in this white paper, we defined the coupled assimilation when we have observation increments in one component impacting the other components. And this can be either at a later stage, meaning in the next data assimilation window. And then we talk about weakly coupled assimilation. It is the case, for example, when we have independent data assimilation system components running, and they interact through the short forecast. So it's one example of weakly coupled assimilation. or they can also, the increments can impact other components during the same assimilation window. Then we are moving towards strongly coupled assimilation. And it is the case when we have a multi-system approach with an outer loop coupling. It's quasi-strongly coupled assimilation. And when we consider a single integrated system, we talk about strongly coupled assimilation, which we can discuss, because if we have a single system, we don't need to do coupling anymore because it's one system. But it's another discussion. So I like the idea of talking about a coupled assimilation continuum. Between no coupling at all and full coupling, we have almost an infinity of possibilities and degrees of coupling, and we can combine also weakly and strongly coupled assimilation method. So there are many different approaches. What we use currently in our operational system, so the last version was implemented in June 2018. We use a weakly coupled land, atmosphere, wave, and sea ice assimilation. We have a coupled background model, a coupled short forecast model for the atmosphere, wave, sea ice, and land. And we are running separately the analysis for 40 var, land, for the atmosphere, land, and wave, and sea ice as well. And then we use the analysis to initialize the short forecast, which in turn provides the background. For the SST, we use an SST product from the UK Met Office, the OSTIA product. This is the case in the current operational system, and it's going to change in the next upgrade that will become operational later this year. So let's focus on coupled land atmosphere data assimilation to start. So it's a weakly coupled assimilation system which is used consistently for reanalysis purpose in ERA 5 and for numerical weather prediction. The land space model we use represents the vertical processes. So we account for snow, evapotranspiration, soil infiltration, and different crops and orography. But the model is working on each grid point independently. And the 2D processes, vertical and time, dominate the land surface processes. And so the land data assimilation system we use is also working for each grid point. This also justifies the fact that we have a separate data assimilation system for land and for the atmosphere, which is a 4D problem. And it gives the flexibility to run land data assimilation with or without coupling to the atmosphere. I will not talk about all the details about the land data assimilation. I just want to focus on the soil analysis and the system we have. Everything red is new and will become operational in the next upgrade, which is IFS cycle 46R1, which will be operational in spring, later in spring. But if we focus on the black part, to explain the weakly coupled assimilation approach we have, we're using a coupled forecast, coupled land atmosphere model, which provides the background for 2-meter temperature, relative humidity, soil moisture at different levels in the soil. So you can see on the top right the different levels in our soil model. And the bottom of this slide represents the observations. So we use in situ observations of 2-meter temperature, relative humidity, and from in situ sign-up data. And we can specialize these observations using a priori 2D OI, which provides analyzed 2-meter temperature used as pseudo observation of 2-meter temperature in our simplified extended Kalman filter soil analysis. We also assimilate, so in black, ASCAT soil moisture on METOP A and B at the moment. And rerun the SCKF to analyze the top 3 layers of the soil. And the analyzed soil moisture provides initial conditions for the coupled background forecast. So this is what we use currently as a weakly coupled approach. And what we developed last year and will be operational this year, to compute the Jacobians, we will use the EDS spread to compute the Jacobians and the relation between the 2-meter temperature, for instance, and soil moisture at different levels. So yes, this is one of the improvements, and this provides more coupling. You see, there is more dependency between the land surface and the atmospheric conditions when we use the EDA to compute the Jacobians. It's still a weakly coupled approach. So one more example to see that weakly coupled assimilation can mean many different things. So we are still using a weakly coupled approach, but with an enhanced coupling with the atmosphere. And another thing which is new is that we developed a smooth neural network product. So we developed a new processor that we implemented last year, which is operational now. And this processor produces soil moisture from the smooth observations. And we will assimilate the smooth neural network along with the ECMWF soil moisture product to analyze soil moisture. So this is just one slide on the smooth neural network product. So we receive in real time smooth brightness temperature. It's an L-band sensor, 21 centimeter of wavelength. And every half an hour, when we have a little piece of orbit, we automatically process it to retrieve soil moisture. And the neural network was trained using the smooth brightness temperature and the ECMWF soil moisture, so that it has mapped the relation between brightness temperature and corresponding soil moisture in our system. So it's implicitly bias corrected. And it allows to retrieve immediately soil moisture from the brightness temperature. So we receive brightness temperature and convert it immediately to soil moisture. So we continuously process the neural network soil moisture to be ready for the data assimilation system, which is shown on the bottom left. It's a soil moisture map processed from the smooth brightness temperature by the neural network and available for data assimilation. So based on this new development, we have a control experiment, which is using the current system, weakly coupled assimilation, with IFS cycle 45R1, where we are computing the Jacobians in finite difference. So I didn't explain here on this slide. In the current operational system, instead of using we don't yet use the EDA Jacobians to compute the Jacobians. Instead, we compute perturbed trajectories for each analyzed variable. And from these perturbed trajectories, we compute the Jacobians. It's very expensive in computing time. And this is why also one of the motivations to replace the finite difference Jacobian computations by using the EDA. So in the control, we compute the Jacobians in finite difference. And we use for observations 2 meter temperature, humidity, and ECMWF soil moisture. And then we have another experiment called smooth here, where on the top of that, we assimilate the smooth neural network soil moisture observations. And we filter out the radio frequency interferences, because maybe you know the smooth product has some interferences, affected by interferences. It's a passive signal which is very low energy level and very sensitive to devices emission at L-band. So we filter these RFIs. And then a third experiment where not only we assimilate the smooth neural network product, but we also use the EDA to compute the Jacobians to replace the finite difference computation. And we run these experiments to different periods, June to August, December to February, and March to September.